Okay, so let's get started. We've just obtained the Cauchy Integral Formula, and now we're going to see some of its consequences. Okay, so let's recall Cauchy Integral Formula. We have F analytic on an open disk, delta, and gamma is a closed curve. Inside delta, given any point Z naught, not on gamma, turns out that the winding number times the value of value of f at Z naught equals 1 over 2 pi I f z minus Z naught dz over gamma. Right? That's where we finished up. Last time. And we made the remark that if the winding number equals 1 in particular, if the winding number equals 1 in some region, for example, if you have some, if you're talking about, it's a simple loop, right? And you're inside the loop, then the winding number is 1 inside there. Then we can express f of z for all z in that region as an integral, right? F of zeta minus z zeta. And so you have an integral that expresses the values of your function in terms of an integral of this guy on the loop, right? So that is, the values of the function on the loop determine the values of the function at every point inside the loop. So this is the first part of the integral formula. Okay, so let's do a couple of calculations using this. The first one is, it doesn't really involve the integral formula, but it's a path deformation example. And it's kind of instructive. So let C be a simple closed curve containing the points 0 and 1. Right? C of the plane is 0 or at least 1. You have some simple closed curve containing it. Somebody asks you to evaluate this, and you've probably already seen some things like this in your homework. How do you do it?
Factor the denominator.
Factor the denominator. Okay. So I've got z minus 1. Right. Got 2z minus 1 on the top. And what are you gonna do with it? You're gonna use what's objective? Anyone know? Partial fraction decomposition. Use partial fraction decomposition and get that this. So via partial fraction decomposition, you recognize that this thing is d over z, 1 over z plus 1 over z minus 1. Okay, so you do partial fraction decomposition, you get this, and then what can you do with it? Well, you can separate it into two. You separate it into two integrals. separated into two integrals, right? And then what can you do with it from here? Right? You're talking about the integral over c of 1 over z, right? So what can you do with it? You can deform the path. You can deform the path so that it's just a circle around 0, right? And then this is just going to be 2 pi I. We calculated that integral before, right? And you do the same thing for this. You deform it into a path. Deform c into a path. So this would be a C1, this would be a C2. You deform it, and you say, well, by path deformation, the homotopy theorem, you know that these guys are homotopic to each other, so you can deform one guy into the other, and you get that this integral, that the integral doesn't change, right? And so you get 2 pi I plus 2 pi I. We saw this integral a long time ago. Or you think of it, this is 2 pi I times the winding number, which is 1. Right. 1 over 2 pi I of this would be the winding number of this curve around 0, which is 1. Is everyone all right? Okay, good. Okay, so that's not really an example of using Cauchy integral formula. The next one is more close to more in the actual spirit of the game. Okay, so let gamma be a circle of radius 0, circle of radius 2. Michael, what's the question? Do you have a question?
No, sorry, we're just saying that, at least in the homeworks, applying Cauchy integral formula, if it wasn't 0, we were usually stuck on what to do. A lot of the time you're stuck, and so for, I guess, this particular instance, since we already know the integral of 1 over c. And so I guess just generalizing that was very difficult. So we're just remarking about that a little bit. It wasn't.
Oh, you mean the use of partial fraction decomposition to
yeah, it wasn't really that relevant. So
okay, sorry. Thank you. Okay, so here's gamma. Gamma is going to be a circle of radius 2 around 0. And somebody says, let's integrate sine z over z squared plus 1 dz over gamma. Okay. So, as usual, the game will be use partial fraction decomposition. Right? So you're going to get via partial fraction decomposition, you get this is going to equal 1 over 2I sine of z 1 over z minus I 1 over z plus I dz from that. Okay. You break this up into two integrals. Z minus I
Read 2I right there, right? And the sample thing.
Right. So what do you get? What is this going to be? Take 10 seconds and write down the answer. What's this going to be? Well, if we had a pi on the bottom, this would be the Cauchy integral formula for sine evaluated at I. Right? So the answer is pi sine 1. and this one's going to be pi sine negative pi. What should you work it out? Turns out to be I e minus 1 using the formulas for what sign is. Okay. Any questions? So using the same gamma. Try to evaluate this I minus z squared z plus I. Easy. Okay. So take a minute or two and see if you can evaluate it. Each of these guys, z minus I, the I lies within the gamma. The negative I also lies within the gamma. The winding number is 1, etc., etc.
Could you have done it using the Cauchy integral formula, but setting f to be like sine of z over z minus I? Leaving. So you get your f of z on top would be sine of z over z minus I, and then on bottom
but it wouldn't be analytic. That function wouldn't be analytic inside the curve.
Okay.
Right? You want your function to be analytic inside the curve. In the interior, you need your function to be analytic in the inside of the loop. But you can certainly do that here for this problem. Okay, turn to somebody next to you and say, this is what I'm using as my f, as my function.
Are they first the partial fractions?
Don't go for partial fractions for this one.
No?
No, actually. No. For this one. Yeah.
So now we're minus 7 maybe 2 against the usual.
This one is a slightly different trick, which is clever choice of f.
Oh, yeah.
Okay.
Yeah.
Yeah.
Yeah. Okay, so what's your f? What f do you choose? F of z is going to be
z over 9 minus c squared.
z over 9 minus c squared, right? Because that one has, it has its singularities here, right? Outside, it's analytic inside, right? So you just rewrite this thing, right? This is going to be f of z over c plus I. Right, so that's going to be 2 pi I times f evaluated at negative I. Right, so you get 2 pi I times negative I over 9 plus 1. That's to say pi plus I. Okay. Last one. So the integral of so you let gamma be the loop around 0 over radius 1, and the problem is to integrate e to the I by z over 2 z minus a half z minus 2. take a minute or so, and what's that?
Yeah.
That's a 2.
Cool.
That makes it a lot easier.
Sorry. Z's are crossed. Okay, so what's the answer? What's the answer, home? I got 2 pi over 3, but maybe I'm wrong. Let me think. Wait.
I got 2 pi over 3.
It's 2 pi over 3. Yeah. That's okay. It's just a minus.
Oh, yeah, okay,
Yeah.
yeah.
Right? Yeah. Okay, right. So it ends up to be 2 pi over 3. Does anyone want to see it? Anyone want to see it? Yeah. Okay. So right. So you take as your f. Like you're looking. You want to. You've got something of radius 1 around 0. Right. So you just look at it and say, okay, well, this function here is analytic there, right? But if I put this thing in, it's not going to be analytic. So that's what I'm going to. So I'm going to take this to some minus 2 as my function, right? I rewrite this as f of z over z minus a half dz. And so it ends up to be 2 pi I f of a half. Right? You evaluate it, right? 2 pi I f of a half. If I put a half here, that's going to be I, right? So I get 2z a half minus 2, right? So 3 halves here. Right? And so I get a negative, thank you. Right? And so I get 2/3 pi. Okay. So you see, this is pretty cool, right? It's not that cool, but it's pretty cool that you can do these integrals, right, in such a simple manner, right? So part of the game the sort of cool part of complex analysis is that you gain this ability to evaluate all these impossible integrals that were kind of tough before. So, okay, so Now, so that's the Cauchy integral formula. There's also something called the integral formula for the derivative. So, integral formula for the derivative. And in fact, we'll have one for all derivatives. There'll be integral forms or formula for all the derivatives. Okay. So we'll state it in sort of from a different point of view. So let C be a fixed contour. Okay. And phi of z, a function continuous along that contour. Okay, so it's continuous on the contour.
Wait, sorry, what's that symbol?
C.
It's just script C.
Phi? This is a script C.
Okay.
This is a script C. I'm sorry, it's pretty close to my zeta.
Why not just remove the little tail?
Oh, no, that would just make it too easy. It wouldn't be a script C otherwise. What would it be? I don't know. Sorry. Okay. Okay. So you have phi, a function continuous along C, script C. We define a function f of z. Wait later until we get to the y stress pay function. Right?
Y stress what function?
The pay function.
Pay?
Yeah. Pay. I'm not sure why it's called pay. It's p, right? But it's called the pay function. Anyway. Okay, so you define a function by 1 over 2 pi I integral over the curve of phi of z zeta minus z d zeta. Then f is analytic on every region containing no point of your curve. And further, the derivative of f can be expressed as f prime z equals 1 over 2 pi I z zeta minus z squared dz. Maybe I should sort of combine two theorems together. So in fact, such an f has derivatives of every order. With the nth derivative being n factorial over 2 pi I, the integral of phi of zeta minus z to the n plus 1 d zeta.
In the numerator of this more general form, you're just taking the single, or is it the nth? Oh, so it's the single derivative. Mm-hmm. Or no, it's not even the derivative. It's just phi. It's
just phi. Right? Yeah, it's just phi. The n shows up in the exponent and in the factorial.
Don't you
need an alternating negative term? What do you use for? If you, well, it's like the n factorial comes from, like as you change, after you take the derivative of that bottom term, the negative power comes up, right? Or,
No.
no, it doesn't? Or why, where does the n factorial come from?
No, I don't think so. I maybe I'm wrong, but I don't. This is a negative number,
Yeah.
and you get also the negative. You
Oh,
get
so
a
they
negative
balance
from
out
the
every
second.
time, okay.
Yeah. Sorry. Yes, it does come from that, but it vanishes. Okay. So so in particular, right? So the previous theorem was saying that if you have an analytic function, then it has some expression, right? Then it has there's an integral formula for that analytic function. Okay. This is stated a little bit differently, right? If you have an integral that defines a function, then that function is infinitely differentiable. Okay. Then that function is infinitely differentiable, and its derivatives also have integral formulas for them. Okay. In particular, analytic functions will do this. Okay. In particular, if you have an analytic function, well, by Cauchy's integral formula, it has, it does have an integral form, and so it's infinitely differentiable. Okay. So this is more general, and it implies a corollary about analytic functions, right? So maybe I should just write it here, right? Corollary. In particular, if f is analytic on some region D, then all higher derivatives exist. Then all higher derivatives exist. Why? Well, because if you're analytic in some region D, then if you take any point, just take a tiny circle around there and use Cauchy's integral formula. Then you have your function expressed as an integral, as the right kind of integral, and the theorem applies. Right? So that would tell you that your function is infinitely differentiable inside that circle. And so every point you can do that. So it's infinitely differentiable at every point in the domain. Okay. So the phrasing of this is a little bit. Sometimes it throws people off, right? How this is related to Cauchy's integral formula, right? Cauchy's integral formula gives you an integral formula for your function, right? And this is saying that if you have an integral formula for your function, then you're infinitely differentiable. Okay, so that's great, right? Once differentiable, infinitely differentiable, right? Unlike the real case. Okay. So let's go for the proof. So we want to show that the limit. How much space am I getting? I'm gonna start from over here because I'm gonna need the whole board. Right. Okay. So proof we want to show that the limit as z goes to z naught, z goes to z naught of f of z minus f of z naught over z minus z naught minus 1 over 2 pi I phi of zeta over zeta minus z naught squared d zeta is 0. Because this thing on the left is the difference quotient that should approach the derivative, and this is our supposed integral formula of that derivative. Okay. So if we can show this is this is 0, we have the formula at that f prime at z naught is this thing.
And you just put that in the limit because it's not affected by z. It's not a function of z. So you can do that.
Say that?
For the second part.
Yeah. Oh, so you're wondering why what are you wondering?
Well, like that, so you have the derivative expressed as a limit on the left part, but then on the right you have an integral which isn't related to, like you're not writing I don't even know what it would look like. Like you're not writing a Riemann sum, which would involve a limit. Like that just is the integral. So it seems to be unrelated to the limit.
Yeah.
Because of that, you're just putting.
Yeah.
You're allowed
It's a constant, right?
Yeah.
Relative to z. Right. There's no trouble of this being dependent on z.
So this is zeta minus z naught squared.
Mm-hmm. Okay, so now let's consider just the first term, f of z minus f of z naught over z minus z naught. Right. Well, we have an integral, by hypothesis we have an integral formula for f, right? That's f of z is going to be phi of zeta, zeta minus c, zeta over gamma minus 1 over 2 pi I. Oops. Phi zeta over zeta minus z naught d zeta. Everything over z minus zeta. Okay, so I'm just expressing, just using the integral formula. Right. Then I'm going to just move the. I'm not going to do anything. I'm going to move the z. I'm just going to combine a little bit. Okay? So phi of zeta, 1 over z minus zeta, 1 over zeta minus c. Oops. Minus 1 over zeta minus zeta. Doing some algebra, some arithmetic. Okay, and then I do more arithmetic. I get phi of zeta over zeta minus z, zeta minus z naught. Okay. Because when you put these together, you're going to get z minus z naught over the product. So nothing is happened, right? Just like you could show this to an intelligent elementary school student, and it'd be okay. Right? Maybe not. Okay. Okay. So now let's look at the limit again, right? So the limit of concern, the limit that we're interested in, then we can write as we're gonna 1 over z minus z, zeta minus c, zeta minus z naught minus, again, we're not doing anything, zeta minus c naught squared d zeta. Okay. We're doing nothing. We're just putting these two integrals together. Okay. And again, we do more nothing. Oops, I forgot the 2 by I. We get z minus z naught, where 2 by I times the integral of the gamma of d of zeta, zeta minus c, zeta minus c naught squared d zeta. Okay. So it's just more arithmetic. Okay, so we actually did nothing at all. Right. Okay. So at this point, we want to control this thing, right? That's what we do in analysis, right? We control things. Let's estimate it, right? Let d denote the distance from z naught to the curve, which I'm writing as gamma, even though I went to all that trouble to introduce the curly c. Sorry. All these gammas should actually be curly c's, but maybe you're happier with them as gammas. Okay. Right. So you have your curve, right, and you have z naught. D is the minimum distance from the curve to z naught, and assume that z is going to z naught, so let's assume that it lies in the half d ball. Okay. So that this is less than half. Okay. So in that case, for all zeta on gamma, right, we know that zeta minus z naught is bigger than or equal to d. Because that's d was the minimum distance from zeta of a zeta to d naught to z naught, and we know that zeta minus z is bigger than a half d, right? Because half d is right. The distance of z to z naught is half d, so the distance of zeta to z must be bigger than half d. Okay, and that's enough for us to get the estimate. So then, if we look at this thing, z minus z naught over 2 pi I. Should I let you finish the estimate? Maybe I should let you finish it. Yeah. See if you can show that the limit goes to 0. Given what you have. Okay. It should take you a minute. Right. Get some bound. Get bounds on the integral and observe that those bounds go to 0. Okay, talk to somebody next to you, somebody nearby, and say what how you're doing it. Home, talk to John. John, talk to home. Okay, home, talk to, I don't know, talk to somebody else. Talk to Alexander. Right, we're trying to show the limit as z goes to z and z naught of this thing is 0. Right. Okay. So let's take the right, so what are we going to use? Triangle inequality, right? This is controlled by what? This integral is controlled by what? Well, the integral of the absolute value, of course. But what is that? What do we get from that? Well, let me ask you this: how are we going to control the 1 over zeta minus z term? This thing is bigger than 1/2 d, right? So 1 over it is smaller than 2 over d, right? This thing is bigger than d, so 1 over it is smaller than 1 over d, right? So you get z minus a naught 2 pi. You have the 2 over d. You have the 1 over d squared, right? And then you have, what about the rest of it? What about the rest of it? You've got this phi. How are you going to control the phi? What do you know about phi? Phi is gamma is some closed curve, right? Or some curve, right? Some finite curve. You've got phi on this thing. Phi was, do you remember? Phi was continuous, right? And so you've got this continuous function on a compact set, right? Continuous function on a compact set. So you've got, it reaches a max, right? So this thing is bounded by some m, right? And then you're just integrating over the length of gamma, whatever that is, call it L. Okay. So that's right. So you get right. So you get that this integral is bounded by z minus z naught times some constant. Right? Times some constant, n times L over pi d cubed. Right? And so as z goes to z naught, then this integral becomes small, becomes arbitrarily small. Okay. So the limit of this thing is 0. Okay. And so this thing goes to 0. Okay. Any questions? Any questions? And this is this typical sort of bounding that one does. You know, you get these lower bounds on these guys, which get upper bounds on these guys. And this is a continuous function on a compact set, so you get an upper bound. Right? Use the triangle inequality. You know, this thing here is smaller than some constant over 2 times the constant over d cubed. So the whole thing is controlled by that constant times the length, times the arc length of gamma, right? Whatever that is. And those are all fixed constants. So, okay. Yeah, Mike.
Could you explain m, where that came from?
M is just the maximum of the absolute value of phi on gamma.
Okay.
So remember that phi was continuous, right? And then this gamma is compact. So you've got a continuous function on a compact set. So the exactly, yeah. So it will attain its bounds.
And then just notation m is just standard notation.
Yeah. We just made it. Right? Yeah, you can call it whatever.
Okay.
So where m is the max of the absolute value of phi, z as the ranges on gamma, and L is the arc length of gamma. Yeah, one often uses an m as an upper bound, and a little m for a lower bound. Okay. Yes.
How do you know you can use the absolute value of the thing inside the limit as an approximation?
So earlier we had something like this, that if you have an integral, then that's over some gamma. That's actually going to be bounded by m times the length, where m is if your function was bounded by some if your function was bounded on gamma, then the integral of the integral of the function is going to be bounded by the bound of the function times the arc length of gamma, and that's basically what we're using here. Okay, so right, your function is controlled by the absolute value of this thing here is controlled by 2m over d cubed, right? And so the absolute value of it is controlled by that times L. That bound by L times L. Okay. So
So for any function, or is it just
for any, yeah. So this is like the triangle inequality, right? The triangle inequality back when the continuous triangle inequality. Okay, so the integral formulas for higher order derivatives can be basically proved in the same way or by induction. It's just more involved, so I'm not gonna do it. Let me show you one sort of contrived application, but no less contrived than all the other applications I showed you. So if you have, say, let gamma be a circle around 0 of radius 2, and somebody asks you to evaluate this. Now you can do it. Right? Now you can do it using your integral formula. Right? This is just going to be 2 pi I over 3 factorial, the third derivative of f evaluated at I, where f is b to the z squared. Right? Just by the third derivative formula. The third derivative integral formula says that the third derivative of this function is going to be 3 factorial over 2 pi I times this integral. Right? So this integral is going to be that. And all you need to do is take the third derivative of e to the z squared and evaluate it at I. And it turns out to be negative 4 pi over 3 dv. Okay. So pretty cool, even if it is contrived. Okay, everyone all right? So now we get like a slew of immediate consequences, all of which are pretty cool. I hope we can get to a lot of them. So a bunch of corollaries. One first is known as Morera's theorem. So if f is continuous in a simply connected domain, f is continuous in a simply connected domain, and if the integral of f is 0 for all closed curves C and D, then f is analytic. So earlier we knew that this was equivalent to having an antiderivative, right? That satisfying this closed path condition was equivalent to path independence and also the existence of an antiderivative. But now your antiderivative is infinitely differentiable, so you are differentiable too. Right? If your antiderivative is infinitely differentiable, if your antiderivative is twice differentiable, you are differentiable, right? But if you are differentiable, you're infinitely differentiable. Okay. So so that's the end of the proof, right? There exists an antiderivative, it's differentiable, so it's infinitely differentiable. So you are too. The end. Okay. So I'm not going to write. Antiderivative is once and thus infinitely differentiable. Corollary. Another corollary about removable singularities. Okay. Suppose f is analytic in the region omega prime obtained by omitting a point from a region omega. An analytic function on omega that agrees with f on omega prime exists if and only if the limit of z minus a f of z equals 0 as z approaches a. So you remove some point A from a region. You can extend f to an analytic function on the entire domain if and only if you satisfy this condition at A. Okay. So earlier we had all these things saying, well, if if this happens, then you can do Cauchy Integral. Now it actually turns out that if this happens, then your function was actually extendable to an analytic function on that whole thing anyway. So it's just a consequence of the integral formula. So let's see, denote a circle around A contained in omega. Then f of z equals 2 pi I c f zeta over zeta minus c d zeta. This holds for all z not equal to A inside C. But we just showed that that integral defines an analytic function G on the interior of C. Right. So if you call this thing G of Z, then that is an analytic function that extends that is an analytic function on the interior of C that extends F. So that gives it to you. Right? That's we obtained an analytic function on omega that agrees with F. Yeah.
Wait, but so doesn't this only, if you said this holds only for z not equal to A,
Yeah.
then isn't G not analytic there too?
G is analytic there. Yeah. So the Cauchy integral formula holds for all z not equal to A.
Mm-hmm.
Okay. Because F isn't defined at A. That's the only reason it's visible.
Mm-hmm.
F isn't defined at A. But this thing on the right actually is defined at A. Even the left hand side doesn't exist at A, but the right hand, both left hand and right hand exist everywhere except at A. The left hand doesn't exist at A. The right hand, however, exists at A, and the right hand defines an analytic function. So that gives you your extension of F to the entire.
Okay, actually, as a follow-up,
Yeah.
then what does it mean to have an analytic extension of another function? Does that allow you to use something on that original function that you couldn't have used if you didn't have this analytic? I guess, yeah, so how do you, what's the significance of this removable singularity?
Just that you can have an analytic function, you can remove certain singularities. Now there are certain singularities that can't be removed, actually. But
okay.
Okay. Okay. Let me let me try to get to some more, maybe more fantastic consequences of Cauchy integral formula. The first one will involve an actually very dull estimate. Okay. So the estimate is dull, but the result is kind of cool. So consequences for entire functions, and remember that an entire function is one that's analytic on the entire plane. So analytic on the whole plane. We have these bounds called Cauchy's inequalities. Let Z naught be some point on the plane. Let C be a circle of radius r centered at Z naught. And let F be analytic on and within C. Okay. And let M sub r denote an upper bound for F, for the absolute value of F on C. This thing of radius r, centered at Z naught. Then we have bounds for the nth derivatives at Z naught. The nth derivative at Z naught is controlled by n factorial m sub r over r to the n. Okay, so what are we going to use? Of course, we're going to use the integral formula for the nth derivative. Right, and in fact, it's a very trivial bound. Fn Z naught equals n factorial over 2 pi I f zeta over zeta minus Z naught and n plus 1 zeta. Right? But over C, right? So we get n factorial 2 pi, and then we need a bound for this, right? Well, what's the size of zeta minus Z naught? That's just r, right? So we get the r to the n plus 1, right? We have a bound for f on C, that's m sub r, right? And then we get the arc length of C, but that's 2 pi times radius. Well, that's it. Right. So all that's involved is the triangle inequality, proof triangle inequality. Triangle inequality plus the integral formula for the nth derivative. Okay, so remark in particular, if we look at the first derivative, it's bounded by mr over r, bounded by the maximum over r. Right? Just take n to be 1. So this leads to the first Liouville theorem. Like I said, that's how we say it in America. Liouville. Okay. The first Liouville theorem. If f is an entire function, I should apologize to my high school French teachers. Sorry, Madame Weiser. If f is an entire function and bounded, then f is constant. Right? That's incredible, right? Or that should be sort of shocking to you. Right? You have a differentiable function that's bounded on the plane. It's forced to be constant. Right? There are no such things except for the constants. Right? Whereas on R, you can certainly have differentiable functions that are bounded, and you can have lots of them. Right? They don't have to be constant. Okay. But, for complex functions, they're forced to be just flat, completely flat. Okay. And the proof just follows from this, right? If you're bounded, right? If you're bounded, then this m sub r is independent of r, right? So there's an absolute constant, right? F by assumption, f is bounded by some absolute bound, right? But then for all r, f prime z naught is bounded by m over r, right? So let r go to infinity, right? Let r go to infinity. You see that f prime is 0, right? The derivative is 0 everywhere, so it's constant. Or, conversely, if f is entire, so saying the same thing, if f is entire and non-constant, then it must be unbounded, right? Then outside every circle, f attains arbitrarily high values. So just rephrasing the same statement.
Sorry.
Yes.
Is that should be less than equal to? We said that with bracket usually. That's it.
Yeah. I mean, it depends on. Yeah. I mean. It depends on if you're thinking of this m sub r as being greater than or greater than or equal to. If you think of it as greater than or equal to, then greater than or equal to. If you think of it as, if you're taking this bound to be greater than, then it'll be greater than. I don't remember what I said. Yeah. So m sub r was just an upper bound. So yeah. So either way. If you're thinking of this m sub r, if you're saying that. If you're thinking of the m sub r as being greater than or equal to, then it'll be greater than or equal to. So I guess I should be consistent. Maybe I should do it this way. I should do it this way. But it doesn't make much difference. You can always make it a little bit bigger, and then it'll be greater. Okay. I might be able to get to the last thing in 1 minute if you let me do it. So let me see. One theorem that's pretty. This is actually trivial. If f is a non-constant polynomial, then given any m, there exists an R such that f of z is greater than m for all z a modulus bigger than r. This is a trivial observation about polynomials. That if you give a bound, you can find given any bound, you can find a circle. Right? You can find a circle outside of which the absolute value of the polynomial exceeds that bound. Okay. That's just because the polynomial is going to head off towards infinity as the absolute value heads off towards infinity, right, if you're non-constant. So I'm not going to prove that. If you want to see it, it's in the notes. The cool consequence is the fundamental theorem of algebra. That if P is a polynomial of degree greater than or equal to 1, then P has a 0. Which is something that you maybe assumed from childhood, but if you're asked to prove it, you don't know why it's true. Here is the cool complex analysis proof. Here's the proof. Suppose P has no roots. Suppose P has no zeros. Okay. Then the function 1 over P is entire. Right? If it has no zeros, well then 1 over it is still analytic. And non-constant. Non-constant. Right, because P was non-constant. Okay. But by the above, there exists an R such that if you're outside of that ring, sorry, P of Z is bigger than 1. We can find a ring outside of which P is bigger than 1. But then, G of Z is less than 1 outside of, right, so in here. Okay. But then G of Z is bounded, right, because G is bounded on the disk of radius r and outside of the disk of radius r. Right? So G is bounded, and so G is constant. Right? Right? So then that's a contradiction because G was non-constant. It's a contradiction. So P has to have a 0. P has to have zeros. Okay. So cool application of complex analysis. Okay, that's it for today. Oh, I forgot to hand back your homework.